Hello world, it's Calcutron here with the first installment of a three-part snake program tutorial. Over the next 3 episodes, we'll be making a simple snake game program. I'll start by demonstrating what the final product will look like. So in this game, you play as a snake that moves around the TI calculator home screen, and using the arrow keys, you navigate this little snake and you try to eat the food, which is represented by the asterisk. And each time you eat food, your snake grows in length, and the objective is to make your snake as long as possible. However, if your snake runs over itself, you then lose the game, and your score is based on how long your snake was at the time that you lost. Now, in my version, you're allowed to go through the walls, and your snake only grows by 1 each time you eat a food. There are a lot of different variations on this game, and if you want to customize it, feel free to experiment with different parts of our implementation. So I'm just going to keep going until I lose, and not to brag, but I'm pretty good, or at least I'm not that bad at the game I created. And so it might be a while, but gradually our snake is getting longer and longer and it becomes harder and harder to keep it alive. I'm not going to lie, this is probably the program that I've got the most use out of all the programs I've written. I've put a lot of time into playing Snake. So hopefully I lose sometime soon and we can get on with this video. But if not, we just might... Oh, okay. There we go. So we got a new high score, and you'll see this also comes with a high score system. And so we got the #1 high score because we've never played Snake before on this calculator. And it also tells us our average score is 39, and we've only played once. So our average is only over 1 game, but over time, I like to compete against myself and try to raise my high score and raise my average. So that is the game we're going to be making. Now I'm going to go ahead and delete it. And if you didn't know this, you can delete programs by hitting second and then memory, which is the second function of plus. And then if you hit 2 and 7, you get to the program memory section. And you'll see our Snake implementation is 508 bytes, which is fairly respectable for a TI basic program, but for Snake it's not so bad. So if we hit delete right here, it will allow us to delete Snake. And now we're going to go ahead and create Snake ourselves. So in this episode, we're going to write the main engine for moving the snake around and detecting collisions. So we're going to start our program with a clear home. That's always the best way to start. And then we're going to right now have a while loop. We'll loop forever while 1. And then we want to first plan out a little bit of how we're going to make our program work. So each frame, each time the snake moves and it gets drawn, 2 things happen. Your snake moves to a new location and the tail of your snake gets destroyed. So, in order to know where we need to draw the new head and where we need to remove the old tail, we're going to need a couple variables. So we're going to use 4 variables to store the x and y coordinates of the head and the tail. And we're going to use x and y for the head. So we're going to start it out at 8 on the x and 4 on the y. So the screen is 8 rows and 16 columns, so this is just about in the middle. And then for the position of the tail, we're going to have it be at 7 and 4, so it's just going to be 1 to the left of the head to begin with. So it's going to start with a length of 2. And then we're going to use the variables s and t for the position of the tail. So s is the x coordinate and t is the y coordinate. And it's common to use s and t as corresponding to x and y because they fall right above x and y on your keypad. So now that we have our positions for the head and the tail, we want to use those in order to draw our snake. So we're going to output at y, x an O, and then we're going to output at s comma t. Well, what we want to do is we want to erase what is currently there, and we do that by outputting a space. And I guess I'll go ahead and put end quotation marks on the one with the space so you can tell it's just one space. Alright, so now we are drawing our new head and our tail, but we want to move our snake. That's the whole point of the game, is to move your snake around the screen. So in order to do that, we're going to have to update our x and our y using a variable for direction. So we're going to have d equal direction, and we're going to start d out as 3, and we're going to say that directions can have the value of 1, 2, 3, or 4, where 1 is left, and then it goes clockwise. So 1 is left, 2 is up, 3 is right, and 4 is down. And I'll get into later why I chose 1, 2, 3, and 4. So we're going to start out d, our direction variable, at 3, which means it's going to be going to the right, which makes sense because our tail is to the left and our head is to the right, and we want to move to the right. So now we want to update our x and y using our direction. And we're going to use something called implicit conditionals. And so what that means is we're going to do x plus a conditional. So x plus d is equal to 3 minus d is equal to 1. So if this is really confusing to you and you'd like to know more about this, you should take a look at the TI Basic tutorial series. But the general principle is, if this evaluates a true, if d is equal to 3, then this will become a 1, and it will be x plus 1. And then if d is equal to 1, it will be x plus 0, because d is not 3, minus 1, because d is 1. So these equals expressions evaluate to 0 or 1, depending on whether they are equal. And then we want to store that into x, and we want to do the same thing for y. So y plus d equals 4, and it's important, even though d equals 4 means down, that actually means an increase in the y, because while it's called y, it's really more of a row and a column, and the y is the row and the x is the column stored into y. And so 1, 1 is the top left corner, and it increases row and column as you go down and to the right, respectively. So sometimes it's a common point of confusion that you would think when you decrease y, you want to go downwards by decreasing y, but you actually increase y in order to move down on this. So this is going to update our x and y with a new direction. So let's go ahead and test this and verify that it moves our snake to the right. And it does, and as you saw very quickly, it caused a domain error. So, but we did see our snake moved to the right. At least the head moved to the right. So that's looking good. Now, what we want to do is we want to have it so that our snake wraps the screen. Now this is kind of a personal preference. I like playing snake. I think it's more interesting when you can wrap around the screen. But I know a lot of people disagree with me and think when you hit the edge you should die, you should lose. So I'm going to show you how you would make it so that you wrap the screen, and then you can choose whether you want to make wrapping the screen make you lose, or whether you want to pursue screen wrapping, or maybe you have another solution. So we're going to do something similar with implicit conditionals. So we're going to do x plus 16 times x equals 0 minus x equals 17. So what this is going to do is, similarly to the line above it, this x equals 0 will evaluate to a 1 when x is 0, and this x equals 17 will evaluate to 1 when x is 17. So when x is 0, it's going to be x plus 16 times 1 minus 0, which is x plus 16 stored in x, and that gives you 16. So when you hit 0, when you've gone below the first column, you wrap around to the 16th column, which is the last column, and then similarly, if you hit 17, it's going to be x plus 16 times negative 1, which is going to be x minus 16, and x is 17, so it's 17 minus 16, which is 1. Now we can actually optimize this a little bit more, and maybe what you see here doesn't look very intuitive to you, and that is true. This is maybe not the easiest code to read, although if you're experienced in TI Basic, you get pretty good at parsing these implicit conditionals. But you might think this is ugly, and you can certainly implement it your own way, but I chose to do it this way for the space saving. And a big part of TI Basic is optimizing for space, and it's good to get practice at that. So another optimization we can do is to use the answer variable. So anytime we evaluate an expression, even if it's a store expression, it's going to store the answer into the answer variable and overwrite the previous answer. And this is a very useful thing to do on the home screen, but it's also useful in a program. So if we know that when we store into x, it's actually also saving that value into the answer variable, we can actually go into this line and replace the instances of x with answer. So let's go ahead and do that. And then we can actually remove this stored into x, and we'll save 2 bytes, because just evaluating this expression on a line will also store into answer. So this will have us wrap the screen on the x, and then we're going to do a similar expression for y. So it's going to be delete this, and then it's going to be answer minus, or let's do plus, answer plus 8 times y is equal to 0 minus y is equal to 9. And for y, it actually doesn't make a difference whether we do this 8 times this expression or we do 8 times this minus 8 times this. I kind of prefer it this way, but for consistency I'll make both of them the same, because for the x it actually does make a difference, because 16 is 2 bytes, and if we do that twice it's 4 bytes. So it works to switch out 1/16 for an extra parenthesis. But irregardless, we have our screen wrapping for the movement of the snake. So if we look now, it wraps the screen, and you can see our tail is actually staying in the same place the whole time at 7,4, or the 4th row in the 7th column, and it's continually erasing the head of the snake that was just there. So it looks like it has successfully implemented screen wrapping, and now we're in an infinite loop, so we'll go ahead and press on and we'll get out of that. And if we hit go to, that's just a faster way to get back into our code. So now we're going to talk about our strategy for updating the position of the tail. We know how to update the position of the head. It's pretty easy. We just use our direction variable. But in order to update the position of the tail, we need to know what direction was the snake going when that tail used to be the head. So where does the snake go next? What's the thing that's one after the tail? And we're going to use a matrix in order to store that information. So we're going to use matrix A, and it's going to be 8 rows and 16 columns. And so we want to have an empty matrix, and one way to do that, well, first things first, we're going to want to store 8, 16 into the dimensions of A, dimensions of matrix A, and that will mean 16 rows and, 8 rows and 16 columns. And then what we could do is fill into matrix A a bunch of zeros, or fill zeros into matrix A, and this would work. But on the topic of optimizations, we've been sort of trying to optimize a lot. We can actually do something slightly more efficient, and because we're filling it with zeros, we can delete matrix A and then store 8, 16 into the dimensions. So when you expand a matrix beyond its current dimension, and after you delete it, it has no dimensions, you can think of it as 0, 0. When you expand it beyond its current dimensions, it fills in zeros. So this will automatically fill in zeros. And then there's another trick that you can do when you use del var, and you don't actually have to put in a line break after your del var. So we can actually delete this, and it will work just fine. Again, not the prettiest looking code. It's probably not quite as intuitive as storing 816 into the dimension of A and then filling it with zeros, but slightly more space efficient, so it's what we're going to use. So matrix A is going to store the direction that the snake was going at each point in the matrix. So we want to initialize this matrix as full of zeros, but we want to tell it that our current tail, which is matrix A at t comma s, we want to tell it that it's going in direction D. So we can do D stored in A at ts, and then it knows at the tail the next place it's going to go is to where the head currently is. Now, when we update our position, we also want to tell it how we got to that position, what direction we went in to get there. So we're going to store into the matrix right here. So we're going to store D into matrix A at y comma x. So now we have a matrix where each position in the matrix tells us when the tail is there, you need to go in direction 3 or direction 2 in order to get to the next position of the snake. So now when we're updating our tail, we want to first, like we have done, draw out a space where the tail is, and then we want to find the next position of our tail. So we're going to use the variable e for the direction the tail is moving in, and we're going to get that out of matrix A. So it's going to be matrix A at t comma s stored into E, and then we're going to do the exact same thing that we did for x and y, but for t and s. So it's going to be t, or we'll start with s because we started with x for our x and y update. We're going to do t plus e is equal to 3 minus e is equal to 1, stored into s, and again this is called implicit conditionals, so you could equivalently have a couple of if statements to do this, but we have sort of an implicit if statement that's doing this calculation. And then same thing with s, we want to do 16 times answer equals 0 minus answer equals 17. So I'm going to speed this part up because it's a little bit of repetitive code to what we just wrote. Alright, so now we've updated our tail to the new position based on what our matrix says the direction of the snake was at that point in time. So now if we run this, hopefully we should have a little snake that moves along, and right now it has a length of 2. So that's pretty cool. We have the very beginnings of our snake program, and we have sort of the core snake moving around engine done. Now I'm going to go ahead and hit on to break out, and just real quickly we're going to test that everything we've written works in all of the different directions. We're going to do that by saying if get key is equal to, let's say, 21, that's the second key. Then we want to update our snake's direction, so later this will be some more complicated code for when they hit the arrow keys to change it to the correct direction. But right now we're just going to have it cycle through all the different directions. So we're going to do d plus 1 minus 4 times d is equal to 4, stored into d. So once again, implicit conditionals. So if d is anything but 4, it's going to just be d plus 1 minus 4 times 0. So it's just going to increment d. And then if d is 4, it's going to be 4 plus 1 minus 4, which is 1. So when it gets to 4, the direction will cycle back around to 1. So if we run this, we're going to be able to change the direction of our snake while it's running by hitting second. And then we can see, ooh, so it looks like we made a mistake somewhere in our program. So it's always important to test at every stage, or as frequently as you can. So somehow our y and our x got a little out of hand. So what happened here? Aha, so this should be minus d equals 2, and then this should be answer. So y actually hasn't been updated, but answer has our next value of y. So now if we run this, and we hit second, it'll turn us, and we can see that that direction's working fine. Then we can turn again, and again, and it looks like our snake is working fine. So this would actually be maybe an interesting snake program, or maybe it wouldn't be interesting, to play where you can only turn to the right, or to the left, depending on how you look at it. But that's all for this episode on Snake, and stay tuned for part 2 and 3. In part 2, we'll be writing the code that actually makes our snake move in the proper directions and allows our snake to grow by eating food. And then in part 3, we're going to add a high score system. So I hope you enjoyed this episode and you learned something, and you're a third of the way to making an awesome, really fun snake program. And like I said, Snake is probably the video game that I spend the most time on. And I really like playing Snake on my calculator. It is a pretty good way to kill time. So I hope that you can get as much enjoyment out of this Snake program as I have. Anyways, if you have any questions or comments, please leave them below. Bye-bye.